Hey everyone, this is Mod 10, Chapter 4. We're talking about the atmospheric convection currents. What you need to know for this is air has four properties that determines why it wants to move. Density, the less dense air rises and the more dense air sinks, similar to why you would have a wood stove in your house in the basement, because the heat rises. Now the water vapor capacity, that's where warm air has a higher capacity for water vapor than cold air, and what that means is warm air can hold water, whereas cold air, when air gets cold, it typically gets compressed together and it really can't hold the water like warm air can. Okay. Adiabatic heating and cooling, this deals with pressure. The pressure of air coming together. So for heating, as air comes together and gets squeezed together, the volume decreases, the pressure increases, and so does the temperature. Now for cooling, as air rises and it expands, it gets cooler due to the volume increasing and the pressure decreasing and the temperature decreasing. Okay, those are related. And latent heat release is when we change states of matter for going from water vapor to water as a liquid form, that you lose some energy there, and energy is released in the form of heat, and it heats the surrounding air. So the air will actually get warmer when water goes from vapor to a liquid. So if we look here at the saturation point, so we have temperature across the x-axis and saturation point in grams per water per meter cubed on the y-axis. If we are at 30 degrees and we change temperature to 10 degrees, what you're going to have is a decrease in your ability for the air to hold water, and then precipitation is going to occur. Now as you go up in temperature, the air can hold more water. As you go down, the air can hold less water. Okay, just gotta read that. Now this is just a phase change where the gaseous state has a lot of energy, water does, and then as we come down to the liquid state, there's this phase change, we lose some energy, and that gets transferred to the atmosphere, and we call that latent heat release. So that's just the phase changes there. Now all these things determine our global wind patterns. So what we have here is the differences in temperature, density, and pressure help the movement. Okay, so let's blow this picture up and take a look at it. What we have here is 30 degrees south, 30 degrees north, and the equator. What's going on is this warm, moist air is rising in the tropics. As it rises, it adiabatically cools. So the pressure gets less, it starts to expand, the temperature decreases, the air can no longer hold water like it used to, so then it rains, and it keeps raining, and that's why we get a lot of rain in the tropics. All right, so then as it comes up, it releases that moisture. Remember, when it releases the moisture, when it goes from a vapor to a liquid, it gets latent heat release, and that air gets hot again and it starts to rise, displacing this cold air, pushing it out, and then as it falls down towards the tropics, what's going to happen over here at 30 south and 30 north is that the air is going to slam into itself, and it's going to do what's called adiabatic heating. That heating, that air squeezing itself down, increasing the pressure, increases the temperature. And then that hot, dry air wants to go back towards the poles or towards the equator, and then go back up and keep cycling again. And that's why we have desert regions around 30 north and south, and then tropical regions in between. Just another slide about hot rising, cooling, condensation, rain falling, latent heat release, cool dry air displaces, falls back down, adiabatic heating, and then the cycle continues. Convection current. So now let's talk a little bit about the Hadley cells, the polar cells, and the Ferrel cells, which aren't up there. But what we're going to look at is where they occur. And notice they're like gears. They work with each other. And then this one, is going like this. okay? And then these are going this way, and then these are going this way. Okay, they're working with each other, okay? Now notice we have dry air coming down here, so this is where our deserts are, and then again we have the air rising at around 60, between this zone and this zone up here, and so more precipitation is going to happen there as well, similar to the tropics. Okay, the Earth rotation, the Coriolis effect. What we have here, it deals with a sphere rotating. And when you look at a sphere and noticing that it's rotating, this distance around the center of the sphere is going to move a lot faster than any point along here. Why? Because speed is distance divided by time, and we know that this point goes around and this point goes around in the same amount of time, 24 hours, but the distance it travels is way different, so the speed of rotation is way faster here, okay? So if we were to throw a ball going straight here and the world wasn't moving, it would end up here. But since the world is rotating and we threw it and the ball is no longer connected to the Earth, it's going to get deflected this way because the Earth is rotating and the ball is going to appear, even though it's going straight, it's going to appear to bend around the Earth. Okay? The Coriolis effect is the deflection of an object's path due to the Earth's rotation. Okay? Now, when you stack this Earth rotation with the Hadley cells and the Ferrel cells and the polar cells, you're going to get some global wind patterns. Okay? These are going to affect our north-south air currents and the way they get deflected. Okay, so we're going to jump into that. Now let's take a look. So we have this Hadley cell, and we know that it's going like this. That makes sense. And the world is rotating like this. Okay, so what's happening as this air comes back down from the 30 north, comes back up from the 30 south, the world's rotating, so it's going to get deflected this way. Okay, and these are called your trade winds. Okay, right here we have your northeast trade winds, your southeast trade winds. Now, this cell, remember, goes like this. So these are going up. These are going up. And these are your westerlies. Now, they're called westerlies because the wind comes from the west. And if you're here in West Virginia, where we are, you can feel and you can look and see our wind and weather coming from that direction most of the time. Okay? Now, these westerlies, and up here we have some polar easterlies as well, down there. So there's like 6 pretty much belts of wind that are global. Okay, polar winds, westerlies, easterlies, these are our trade winds, more westerlies than polar easterlies. So the differential heating of the Earth's surface, the rotation of the Earth, all help provide trade winds, or the wind direction. Okay, rain shadow effect. This is the windward side, this is the leeward side. As this warm, moist air comes up, it gets cool, dropping precipitation, and then the dry air, cool, falls down, gets adiabatically heated as it gets compressed, and it warms and becomes dry. So that's the interesting rain shadow effect.